Hey guys, so today we're going to look at IP version 4. Internet Protocol version 4 is the most common, still most commonly used logical addressing on the internet. In spite of the fact that IPv6 is available and is needed, people still haven't switched over to IPv4 yet. So let's go ahead and look at it. IPv4, Internet Protocol version 4, is a unique 32-bit numeric address divided into 4 8-bit octets. What that means is 32 bits, 32 total characters can be either a 1 or a 0 in binary. And we generally look at those in regular numbers in base 10, and so there are 4 8-bit octets, which means 4 numbers between 0 and 255 separated by a period. So an IPv4 address is displayed in dot decimal notation, but stored as a binary number. For example, 192.168.12.1 is stored as 11000000.1010000.00000110000000001. So it's stored as a binary, but it is displayed as a octet or 4 8-bit octets. An IPv4 address is used at the OSI model's network layer to uniquely identify a device on a network. Similar to a MAC address. As you recall, last time we talked that MAC addresses had the last half of the 48-bit MAC address. You've got 24 bits up front that belong to the network or to the manufacturer, and then you've got 24 bits, the back numbers, the last 6 digits or 6 characters belong to the device itself, uniquely identifying that device. Well, an IPv4 address does the same. The first portion, based on what type of network you're working on, whether it's class A, B, or C, the first portion of the address belongs to the network. That means it all has to be identical. The last portion of the address belongs to the device. That means it has to be unique. And in that way, each device is given a unique location identifier on the same network. A loopback address, also called the local host, is an internal address that routes back to the local device. So IPv4 loopback address is 127.0.0.1. That is traditional. That address cannot be routed on a private or a public network. 127.0.0.1 is always going to be a loopback address. So if you ping that, you're going to be pinging your internal device. Got a participation activity here. Another participation activity in the subnet mask. That is a 32-bit number. Looks just like an IP address. It's used to divide an IP address into host and network portion. The host portion belongs to the individual computer. The network portion belongs to the network. And that's what gives the address its uniqueness. The host portion always has to be unique. The network portion always has to be the same for all devices on the network. Subnet mask defines the range of hosts available. So a subnet mask basically tells the rest of the network what part of the IP address is network and what part is host. The IP address network portion identifies the network in which the host resides. So every single address on that network has to have the same network portion. Otherwise, it can't communicate. Then the host portion identifies the host within the network. This has to be unique for every single address on the network. Otherwise, you have an IP conflict. You have duplicate IP addresses. If you do that, then one or both of those hosts will be kicked off the network. And then once again, we have a participation, another participation address. Classful addressing, class A, B, C, D, and E. That's IPv4 addressing architecture that classifies networks into 5 classes. The 5 classful classes are class A, B, C, D, and E. The first 4 bits of an IP address contain the first 4 bits, of an IPv4 address determine which of the 5 classful addresses the IPv4 belongs to. A, B, and C are used for device addresses, and D is used for multicasting. E is reserved for future use, which probably will never ever be fulfilled now since IPv6 is being used. Each address is defined by a subnet mask. Remember we said a while ago, the subnet mask is basically it's a pattern that tells the network what part of the address belongs to the network and what part belongs to the host. So a Class A IPv4 address uses the first 8 bits, and the remaining bits belong to the host. So essentially the first octet belongs to the network. So the only thing that has to be the same on the network is the first section. The subnet mask for a Class A looks like that, 255.0.0.0. The portion that is 255, that first octet, has to be the same. In fact, that's the way subnet masks work. The portion of them that's 255 has to be the same. The portion of them that's 0 can be anything. And then based on subnetting, which we'll talk about a little bit later, this number doesn't always have to be 255 or 0. It can be other things. But for right now, this portion, the first octet, has to be the same on a Class A network, and then you have a lot of available host address. So a Class A network can have a lot of hosts, like 16,277,214 hosts. That's how many available devices can be on the network. A Class B, that uses the first 16 bits, goes to the network, and the remaining bits go to the host. So your subnet mask looks like this. The first 2 octets are 255. The last 2 are zeros. 16 bits for the network, and then you can have 65,534 possible hosts in a Class B network. Class C, as you might expect, the first 3 octets belong to the network, so all 3 octets in a Class C network have to be the same. The last octet belongs to the host, which means that the last octet designates individual hosts on the Class C network. You can have, there are 24 bits that belong to the network, and then only 254 addresses belong to the host. So you can only have 254 individual devices. You subtract 2, you'll notice it's got 2 to the 8th minus 2, 2 to the 16th minus 2, 2 to the 24th minus 2, and so on. The reason you're subtracting is because the first and the last address in these groups are designated. They are specific, and you can't route them. So you're going to lose 2 addresses from each octet, or from each group of octets based on the class system. Then Class D is multicasting. Does not have a subnet mask per se. And Class E is reserved. They've been saying that for years, reserved for future use, but it's never been used. It's never been implemented. So there is really no such thing as a Class E address, to my knowledge. The size of the host supported is the problem with classful addressing. 4 Class C networks are needed to accommodate 1,000 network devices. And that's a tiny network, really, compared to some corporate LANs. Using multiple Class C networks impacts efficiency because you have to adjust routing tables to account for the different network portions of the address. Using a Class B network is only 65,000 hosts per network, and that wastes 64,000 potential host addresses. Class B networks are initially used to improve efficiency and speed, leading to a waste of addresses and a need for subnetting. So these are old problems. In fact, nowadays, the main problem with Class 4 or with IPv4 is that there just aren't enough numbers. Their networks are so huge now that you could technically use 16 million addresses. So networks are too big, and there are just not enough numbers, particularly for internet routed addresses. When we talk about public and private IP addresses, private IP addresses are usually not a problem to use IPv4 because, like I said, 16 million is a lot of hosts. That's usually enough. But when you're talking about IP addresses that are routed on the internet, there are a lot more than 16 million devices out there. And so essentially we're out of numbers. And that's why we moved to an IPv6 model, which is a much, much bigger model. It has a lot more information. We'll talk about IPv6 momentarily. Got participation activities to complete. Okay, public and private. We just mentioned that just a moment ago. A public IP address is an IP address that can be routed on the internet. That means it can be routed on the public internet. It's assigned by an internet service provider and is unique to each host, whereas a private IP address is a local address inside a private LAN. Private IPs communicate across a specific network, where a public IP communicates across the whole internet. Initially, ISPs assigned companies classful addresses, leading to potential IPv4 waste. The limit for IPv4 addresses is 2 to the 32nd. It's about 4 billion addresses. Using classful addressing produces an IPv4 shortage. So private IP addresses was developed to alleviate that problem. Now we've run out of even that solution. So ISPs assign one IPv4 to a company, and that company then uses routers to break that network up into smaller pieces. So they have private IP addresses behind the router, and the router is a public-facing public IP that can be routed onto the internet. Then the router performs network address translation, or NAT, which we'll talk about a little bit later. And so it keeps up with, as the packets go out, it changes the IP address inside the packet to the public address. They go out, they get routed, and then they come back, and the router changes the public address that's now inside the packets back to the private address that was there originally, and then it routes them internally. Company's phone system has one unique outside number, but many internal extensions. The outside number is the public IP. The internal extensions are the IPs, or private IPs. That's a kind of an analogy. So public IPs are class A, B, and C. And the public IPs can go 1.0.0 to 9.255.255, so on. And then we skip 10 dot because 10 dot is class A private. So we skip all the 10 dots, and then we go to 11 up to 126. You'll notice we skip 127. We go from 126 to 128 because 127, as we learned a while ago, is the loopback address. You can't use 127 for anything. So we use 128 to 172. Those are Class B publics. And 172.32 to 191.255. That's the other half of the Class B publics. And then Class C public addresses are 192.1.0 to 167. You'll notice we don't use 192.168 because that's the Class C private addresses. And so we skip over to 192.169 and we go to 223.255. Then the private tables, all the range that we skipped in the publics are assigned to the privates. So Class A private is 10.0 to 10.255. Class B is 172.16 to 172.31. Class C is 192.168 to 192.168. And that is both public and private classful addressing. You have another participation activity and a challenge activity, and that covers IPv4. We will look at IPv6 in the next video. If you have any questions, let me know. You can contact me via the Canvas inbox or ask me in class, and I will do my best to answer those for you. Have a good day.